In our second lecture, we're going to take a look at the history of astronomy. Now necessarily this will need to be a fairly brief history. I obviously won't be able to cover great details in all of the various discoveries that were made, but I'd like to give you a broad context of how we came to our understanding of the universe today. I also won't be able to explain every discovery in this particular lecture, but as we move along into the next lectures, I will be able to go back and again give you a much more detailed explanation. In this lecture, I'll merely be describing what was found. When we go back to the most ancient cultures, we find that humans were always looking at the sky. We think of cultures such as ancient Assyria and Babylon, Egypt, and others. Now, in these early times, we were by no means doing science as astronomy, but rather people were merely noticing what was in the sky, and frankly they were somewhat superstitious and often attributed it to supernatural beings and so forth. But they were looking at the sky and taking note of what they saw. In later centuries, other cultures, perhaps in Europe, in the Far East, and even in the Americas as well, were looking at the sky. We find that from various records that have been left behind, showing different constellations and star almanacs and certain things of that nature. What were some of the things that they were able to discover? Well, they noticed, of course, the daily motions of the sky, the monthly cycles of the moon. They noticed the sun getting higher and lower in the sky. And all these things intrigued them. They didn't have an explanation for them. Even a few of the stars, what they thought were stars, the brighter ones, were moving, slowly drifting. And these became known as planets. They even were able to notice different eclipses and realize that these recurred periodically. Well, in time, they began to think of ways that they could use this knowledge effectively in their life. For example, they began to learn how to track time and seasons, make calendars so that they know when different events were going to take place. Now, certainly there were, again, these religious and ceremonial purposes, perhaps to various religions, but the point being there was also some very practical sides to that knowledge as well. For example, most ancient cultures depended heavily on agriculture to grow their food, and they wanted to be sure to know when was the best time to plant the crops, so that as the seasons changed, the crops would grow, they'd have food to eat. In fact, some early civilizations even used their knowledge of the sky to help them in navigating. We'll talk about that a little bit more, but for now, you might know that as you travel north and south on the Earth's surface, the constellations appear to shift their position. You might even be familiar with the North Star. As you watch that carefully in the northern hemisphere, it gets higher in the sky the farther north you travel, and it gets lower in the sky the farther south. So the point being that you can get a rough idea where you are simply by looking at the North Star. Well, after some centuries of this, one culture began to arise that really kind of stands out in many ways, but in particular for our discussion in astronomy, and that was ancient Greece. As Greece rose to power, they became known for their studies in many fields. We think of their literature and philosophy, even their mathematics, such as geometry and things. But the Greeks became very good astronomers. And the reason they were especially important is because that was the first place we begin to see the scientific approach to astronomy. Now, the Greeks, of course, observed the sky as earlier cultures had, and they began to develop one of the very first models of the universe. They certainly felt that the Earth seemed to be the center of everything. And frankly, it does appear that way, doesn't it? Interestingly, some of the early Greek scholars even knew that the Earth was spherical. We often assume that all ancient people thought the Earth was flat. That's not necessarily true. Some of their scholars realized it was spherical, and they placed this spherical Earth in the center of the universe with all the other bodies orbiting around them. Now, they also made an assumption that later on proved to be rather significant. Because they felt that the heavens were perfect, they assumed that the orbits of the bodies in the heavens had to be perfect circles, because to them that was the perfect geometrical shape, very uniform, very symmetrical, and so they assumed that the orbits in the heavens were circular as well. But there were three things in particular the Greeks did that, again, we really point to today as showing us that they were adopting that scientific approach. Number one, they began to try to explain what they saw in the sky without resorting to their mythology or supernatural explanations. And this is what scientists do today. Number two, as I mentioned, they began to build models of nature, and these were based on their observations. As they would watch the moon move through its phases, they might think, well, the moon appears to be going around the earth, and it's probably illuminated by the sun, and that's why we see the phases. Finally, the Greeks became known for reasoning on their observations with each other. They would have great discussions, much as they did with their philosophy and other fields, and talk about the things that they saw and observed and discovered. And yes, they put their math to good use as well, using geometry to explain what they saw in the sky. After some time, one particular Greek astronomer began to rise above the others, so to speak. By the 2nd century AD, Claudius Ptolemy appeared on the scene, and Ptolemy took it upon himself to begin to take all of the known astronomy of that time and to compile it. He wanted to document this all. Different astronomers had learned different things. He said, I'm going to take all of this and I'm going to basically document it. And he did an outstanding, comprehensive job of doing that. He wrote a total of 13 different volumes on the known astronomy of his time. He touched on things such as the constellations, the celestial sphere, the motions of the moon, the motions of the sun, eclipses, on and on these books went, and it really did become quite a comprehensive work. Now this, of course, was a good thing. It not only brought all this information together in one place, and therefore enabled others to learn, but it standardized their learning. And in this way, many people could be learn about astronomy. However, there was one particular aspect that tended to be more of a negative thing here, and that is the fact that Ptolemy did such a good job that many people didn't feel it was necessary for them to maybe go out and do so much observations, or for them to think about building new models, or for them to pursue further investigations. And so this had the effect of tending to stifle progress in astronomy. Many people felt if you wanted to learn about astronomy, just read Ptolemy's volumes and you'll be done. And unfortunately, again, many did that, and as a result, again, progress was somewhat stifled. Well, Ptolemy's works grew and grew in their stature. Ptolemy began to be revered as the primary figure in astronomy for nearly 14 centuries. His work in astronomy was considered the authoritative summary. Well, you may know that, of course, the Greek civilization declined and was overtaken by the Roman civilization, and for several centuries the Romans then held sway, but eventually Rome fell. Europe entered into the Dark Ages. There wasn't a lot of learning and science done at that time. But fortunate for us, another civilization did preserve that knowledge from the ancient Greeks. Islamic scientists were very curious and very interested in the Greek understanding. They took those writings and they preserved them and they translated them into Arabic, and for centuries, so to speak, held that knowledge for us here in the future. Now, they didn't only preserve and copy the information from the Greeks. No, these scholars were quite capable themselves. They certainly had an idea of how to do their own research. They improved timekeeping, navigation by the stars. They developed a few instruments such as the sextant, which in future times sailors would use to measure positions of stars. And they developed somewhat of an interesting device called an astrolabe that was sort of a miniature model of the solar system. The bottom of the astrolabe would have a metal disc with the stars and constellations, and on top of that would be other discs that could be turned in a way to align with the planets or the moon or the sun. And in a sense, then you'd have a miniature version of the solar system in your hands. So quite a useful device. Many of these are preserved in museums today. So again, for a number of centuries here, These scientists preserved, extended, improved our knowledge of astronomy. Now, like the ancient Greeks, they still believed in an Earth-centered universe, and they refined that to the point that it was pretty much as good as it was going to get. But we have them to thank, again, for preserving that information. At some point, of course, as Europe now began to come out of the Dark Ages, European scholars were interested in their writings. They took those Arabic works, translated them into Latin, and Latin, of course, led to many of our modern-day languages. So here matters stood toward the 14th, 15th century, and yet a few astronomers had noticed that there were a few nagging problems with Ptolemy's conception of the universe. In other words, as you would look up and watch perhaps the planet Mars as it's moving week by week by week, it never quite corresponded exactly to Ptolemy's best model. Or maybe I should say that the other way around. Ptolemy's model never quite corresponded exactly to what was really happening. So at some point people began to say, maybe we need to look at something else. Well, you may have heard the name Nicholas Copernicus. Copernicus was the first to really stand up and suggest a different way to look at the universe. Now, this was quite a change. For centuries, humanity had just assumed the Earth was the center of everything. Few, if any, questioned it, as it seemed so very obvious that the Earth was the center and everything moved around us. But Copernicus revived an idea that had been mentioned centuries earlier in ancient Greece, that perhaps the sun was the center of the universe, and perhaps the Earth was moving around it. Now, Copernicus was very cautious in publicizing this. He knew he'd be ridiculed. In fact, even the book that he wrote on this topic, he delayed its publication until much later in his life. Much of the resistance was because the intellectual climate simply stated that Earth was the center of everything, that humanity was the center of everything. So it's really quite a revolutionary idea, a whole new paradigm for us to try to absorb and accept. And frankly, in the beginning, there wasn't a lot of proof for that particular view of the universe. But about this time, shortly thereafter, another important figure appears on the scene. His name is Tycho Brahe. Now, Tycho Brahe was a Danish nobleman, and he very much wanted to observe the sky. By this point in time, not so many people were doing that, but he wanted to go back and do a very expert, first-rate job of observing the sky. So he talks to the king, and he obtains some funds. He builds really one of the world's first observatories. Now, he doesn't have a telescope, but he does invent some instruments that allow him to carefully measure positions of stars, the moon, the planets, to better accuracy than ever before. Brahe does a tremendous job. For over 20 years, he makes these very exacting, very precise observations. He does what we would today say, collect data or observations that, again, could be used. What does he find? He finds that the existing predictions of Ptolemy's Earth-centered model are simply wrong. You cannot recognize or reconcile that model with what's happening. So here was a turning point now. It becomes very obvious through his careful observations that our understanding of the universe is going to have to change. It simply doesn't work anymore. Well, Brahe's done an excellent job of observing, but another man appears on the scene now who is very good mathematically. And he recognizes the value of what Brahe's done, and he'd like to get access to Brahe's records and use them to try to establish, again, this new sun-centered model of Copernicus. This man's name is Johannes Kepler. Now, Kepler eventually gets some access to Brahe's data. Brahe's a little cautious about giving him all the information, but as time goes on and he obtains the information, he begins to try to fit orbits to Mars and other bodies, and he as well realizes that you simply cannot fit a circular orbit to Mars. Well, he has a choice now. Either he trusts that Brahe did a good job, or he goes back to still sticking with the old model of Ptolemy, which, again, is becoming increasingly inaccurate. Well, thankfully for us, Kepler very bravely says, no, I do trust Brahe's measurements, and this is telling me that the planets do not move in perfect circles. Rather, they move in ellipses. Now that may not seem all that important to you and I, but it really opened the door to breakthroughs in astronomy, because Kepler is then able to go on and determine that when the planet is closer to the sun in its elliptical orbit, it moves faster. And when it's farther from the sun, it moves slower. This finally explains why Mars' motion doesn't match the Ptolemy model. So this is a significant advance. Kepler goes one step further and discovers yet another law that relates the period or time for the planet to orbit and its distance. And this third law of planetary motion is a law that astronomers have used to this day and continue to use to help us understand the motion of planets. About this time, another important figure arises on the scene. Perhaps you've heard the name Galileo. Galileo dramatically changed our view of the heavens because you might know he was the first to use a telescope to observe the sky. We don't think that he necessarily invented it, but when he saw one, he went home and made himself one and improved it and turned it on the sky and saw things no one had ever seen before. He saw craters on the moon, as we'll see in a minute. He saw moons orbiting Jupiter, phases of Venus, so many wondrous things that had never been seen before. Now Galileo was very excited to share this with others, but many were quite skeptical because, again, the intellectual and even the religious climate at that time was somewhat rigid and believed in a certain view of the universe that Galileo's observations were beginning to challenge. But the key for us is that his observations provided the proof or the evidence for the sun-centered model of Copernicus. So this led to great advances as time went on. Others began to get telescopes, look at the sky, and begin to see some of these things. And gradually, these ideas took hold. Some decades later, yet another important figure comes on the scene. I'm sure you've heard the name Isaac Newton. Now, up to this point in time, most astronomers, again, are merely describing what they see. They really can't explain why different things would occur, but they could tell you what they did see. For example, Johannes Kepler could tell you how the planets move, but he really couldn't tell you why they move that way. Well, Isaac Newton is now going to explain further why we see what we see. Newton begins to learn about motion, establishes 3 laws of motion, and realizes that these apply in the heavens. He also correctly learns about, as we mentioned earlier, the law of gravitation. And he applies this not just here on Earth, but again in the heavens. He correctly realizes, according to his laws of motion, that the moon should be moving on a straight line, and yet it's not. It's curving around the Earth. And when he thinks about why that would be, he realizes the Earth must be exerting a force that keeps the moon in its orbit instead of allowing it to travel at a straight line. So again, you see the equation and the diagram of the law of gravity, and we emphasize that Newton went beyond describing what we saw up there, but he began that first steps at explaining what we saw up there. Why does the moon move around the Earth? It was because of gravity. So in the succeeding decades, astronomers, again, slowly, gradually improve their telescopes. They begin to see, for example, again, moons around Jupiter, rings around Saturn. But at first, their telescopes really only allow them to explore the solar system. It wasn't until the late 1700s that a very important observer appears on the scene, and this man's name was William Herschel. William Herschel really proved to be pretty much the most important observer of the 18th century. Why is that? Well, Herschel was dissatisfied with the poor quality of telescopes in his day, and so he built better ones. Instead of using lenses, which were somewhat imperfect at that time, Herschel switched over to a design by Isaac Newton that used mirrors. He was able to make the mirrors bigger and therefore the telescopes bigger. And he was able to see things beyond the solar system that others had never seen as well. So Herschel built these huge telescopes. He spent many countless evenings under the night sky, essentially sweeping the sky, looking for objects that he could observe. And he made our first systematic catalog of these different objects at the end of the 1700s. He had found hundreds of them. And frankly, this was the first time that humanity was able to see these. So this, later on, would lead to great advances as well after we had done a first survey of the sky. Well, as we moved into the 19th century, there were certain questions that, of course, humans had wondered about for ages. What are the stars? How far away are they? How big are they? What are they made of? All these questions remained, and astronomy began to provide answers. The first important discovery was the distance to the stars, and again we'll see more in a future lecture. But for now, what we essentially want to discuss is that nearby stars could have their distance determined if we observe their apparent position at one point in time when the Earth was on one side of the Sun in its orbit, and 6 months later when the Earth was on the other side of its orbit, we would get a slightly different view or slightly different perspective of that nearby star. In effect, it would appear to shift position relative to the background stars. Well, some simple geometry would allow us then to determine the distance. The angle that that star appeared to move in the sky could be used, again, to determine its distance. So we'll come back and talk about this again. The actual term was parallax, and this enabled astronomers to first get an idea in the mid-1800s of the distances of the stars. They had to invent a new unit called the light year, 1 light year being approximately 6 trillion miles, and the nearest stars turned out to be perhaps 10 or 20 light years. So quite a great distance that humans had never really considered before, but we now had some idea the distance of the stars. Well, as time went on, astronomers continued to observe the stars, and they focused in particular on occasions when they would notice two stars appearing very close together in the sky. They suspected, and were correct, that these stars were orbiting around each other. And this, first of all, proved that Newton's concept of gravity operated among the stars. Well, as we'll see in our future lecture, observations of these two stars' orbits, the distance between them, and the amount of time it took them to orbit, could tell us the masses of the stars. In other words, how much material does each star have? And this would open the door and allow us then to discover other characteristics of the stars in the future. So this was a very important task for 19th century astronomy, was to carefully measure the orbits of these binary or double stars, and that led us to an understanding of the masses of those stars. That really became, as I said, the foundation for other important discoveries. Towards the end of the 19th century, astronomers began to make use of a discovery to tell us the composition of the stars. It had been discovered that if here on Earth you took certain elements and burned them, why the light that they gave off, if you broke that light into a rainbow or a spectrum, would have certain lines in it, some dark, some light, and those lines were a very unique pattern that corresponded to that element. In other words, if we heated up a certain substance, looked at its light, broke it into that spectrum, those lines indicated, again, the identification of that particular element. Well, I think you can see that we could do something similar with the stars, couldn't we? And again, towards the end of the century, astronomers began to do this. We take the light from a star, and we carefully break it into a spectrum, and we look for those lines, and those lines tell us the elements present in the star. So quite an ingenious way for us to be able to determine the composition of stars without ever going there or trying to get a sample of them. So we'll talk more about that in a future lecture, but this was a major breakthrough to understand what the stars were made out of. Some of the objects that astronomers had cataloged, such as William Herschel, appeared to be glowing clouds of gas out in space, and sure enough, when astronomers took the light from those clouds and again broke it into a spectrum and looked at those spectral lines, they were able to confirm that yes, indeed, these were clouds of primarily hydrogen gas with some helium and a few others mixed in. But this told us that the bulk constitution of the universe was hydrogen. Later on, we're going to see that some of these beautiful objects, some of these clouds, often glowing, are where stars are forming. And so this led to another whole subfield of astronomy to talk about the formation or the birth of stars. So these nebulae or clouds became a subject of intense interest in the late 19th, early 20th centuries. There were a few different types. Some again appeared as just clouds, others were smaller and rounder, planetary nebulae. But as astronomers began to do their research, they began to identify the composition of these objects and learn what they really meant for us. As we moved into the 20th century, astronomers began to see the differences in stars, that they had different characteristics and properties. But at first, we merely wanted to sort them into various categories, so to speak. And this was somewhat tedious, laborious work, but again, it was important for us to lay that foundation. And as astronomers began to examine those early classifications, they began to realize that stars don't come in all combinations of brightness and temperature. You might think that, strictly speaking, the hottest stars would be the brightest, and that was generally true, but there were important exceptions to that. So early in the 20th century, two astronomers devised a chart, which you'll see in the slide here, and this became known as the Hertzsprung-Russell diagram. This diagram, the HR diagram, proved to be a key to understanding the lives of the stars. So we'll see much more of it in a later lecture where we'll put it to use and we'll use it to understand the lives of the stars. Again, many stars are related by their brightness and temperature, but there are exceptions, and as a result, astronomers began to learn that they were not all the same size. Some were much larger, giant and supergiant stars. Some were much smaller and became known as dwarf stars. So we'll be back later in the course to examine that in much more detail, how we can use that diagram to understand the stars. As we moved into the middle decades of the 20th century, a real outstanding discovery took place. You've probably heard the name Edwin Hubble, and Hubble was the first to use the large telescopes of his day to look out at some of those nebulae and find that not all of them were clouds of gas. Instead, Hubble was able to make a discovery that changed our view of the entire universe. Earlier, a female astronomer, Henrietta Leavitt, had found the distance to an object just somewhat outside of our Milky Way galaxy, noticing the variations in stars' brightness and using those to get an idea of the distance. Well, Hubble took that technique and he applied it to other objects that he suspected were outside our galaxy, and sure enough, that's exactly what he determined. At the time, there was known the great spiral in the constellation Andromeda. Hubble very patiently and tediously observed that object, found those stars changing their brightness, and was able to determine its distance at over 1 million light years. Today, we've actually revised that number upward. We know that that particular object is approximately 2.5 million light years away. But this was the first evidence, the first proof of a galaxy beyond the Milky Way. So this really expanded humanity's perception of the universe to know that even our Milky Way galaxy was not all there was. Well, Hubble wasn't finished yet. He made a second huge discovery. As he was starting to look at a few other of these objects and determined that in fact they were galaxies outside of ours, he noticed something very interesting. By carefully measuring the galaxy's spectral lines that we talked about, we take the galaxy's light, break it into that spectrum, look at those lines, he could get a real good idea of the speed or velocity of the object towards or away from us. And he noticed that nearly every galaxy was moving away from us. This seemed very odd. Why weren't they just all randomly moving? Well, he began to realize what this implied. There was a direct correlation between the distance of the galaxy and its velocity. In other words, the farther away the galaxy was, the faster it was moving away from us. Well, this implied something very profound, didn't it? If you think about that for a minute, if it appears, at least to us, that all the galaxies are moving away, that would imply the universe is expanding. And so this was the first evidence that told us the universe was expanding. Well, you take that even one step further and say if the universe is expanding, surely that means that in the past it was smaller. And as a result, if you go back far enough into the past, the universe will be very, very small and had to originate in a single point, which today we call the Big Bang. And this is really the prevailing theory about the history of our universe today. The Big Bang theory began with Hubble's discovery of an expanding universe. So what a change in our view of the universe. Well, we've sure covered a lot of ground, haven't we? Let's do a summary and review some of the things we discussed. We started way back centuries ago, millennia ago really, looking at the very earliest cultures, looking at the sky. They began to get a knowledge of the sky. The ancient Greeks developed this Earth-centered model that seemed to work for a while, but some centuries later, Copernicus, knowing that that model was imperfect, proposed a sun-centered universe. Today we know that the sun is the center of our solar system, not the entire universe. And it was Galileo's telescope that really provided the proof. When he saw moons orbiting Jupiter, when he saw the phases of Venus, that indicated that Venus had to be orbiting the sun. It could not be orbiting the Earth. We then moved through more recent centuries where astronomers determined the distances of stars, then their masses, then their compositions, and their temperatures. And finally, in the 20th century, we saw that Edwin Hubble not only showed that there were galaxies outside the Milky Way, but he showed that they were expanding away from us, and this implied an expanding universe which began in a Big Bang. So quite an exciting story. What a grand sweep astronomy has showed us now, and the discoveries continue to come today, as we're going to see in future lectures. So I look forward to sharing more with you in our next lecture.